So good morning, guys. Today we're going to jump in and start our discussion on heat transfer. And so today is really just going to be an overview of heat transfer. We'll discuss the types of heat transfer, the key characteristics that we see. And then on Wednesday, we'll do a deeper dive into conduction, which will probably last the rest of the week. However, as it applies to chemical engineering and heat transfer equipment, we spend a majority of our time in this essentially main module of heat transfer focused on convection. However, conduction and radiation are still as important. So an introduction to heat transfer. We can't have a discussion of heat transfer until we understand what is heat. So if I asked you what is heat, what would be your response?
The kinetic energy of atoms.
Yes and no. Heat is derived from the kinetic energy that exists within atoms. So you're close, you're halfway there.
Stored energy?
Not necessarily, that would be internal energy.
Thermal energy.
You guys are all on the right track. Let me put it together. I would state heat exists as an energy transfer. Between matter, substances, objects, due to a temperature gradient. So the key concepts here is that heat exists as an energy transfer. And the driving force for that energy transfer is the existence of a temperature gradient. So you were on the right track when you were talking about molecular kinetic energy because we express that as temperature, not necessarily as heat. Heat emerges due to the gradients that exist within the temperature gradient, right? And we also call this the driving force for heat transfer. And so heat is always transferred or I should say heat always transfers from a high temperature to a low temperature. And so these are just kind of some, really key things that I always want students to keep in mind, right? Heat is an energy transfer. The transfer exists due to a gradient. That gradient, when it comes to heat, is temperature. Just like fluid going from a high pressure to a low pressure, heat always transfers from a high temperature to a low pressure. Another thing I always like to say is, heat exists, cold does not, right? Cold is essentially the absence of the energy transfer. And so in thermo, you're often concerned with the necessary amount of heat that exists within an energy balance. However, in this class, when it comes to heat transfer, we are concerned about the rate of heat transfer. And so in mechanical energy balances, heat is designated Q. So in this class, what we're often looking for is Q dot. Or if Q is in joules, Q dot is going to be in watts or BTUs, your hour. So what we're often concerned is the rate of heat transfer. We want to know how quickly heat is transferred or as it relates to heat exchangers and design principles, how much area or heat transfer area is required. Work. Which we're interested in understanding area. One thing we can consider is not necessarily just the heat transfer rate, but the heat transfer rate per unit area, which we call a flux or a heat transfer flux, which I designate lowercase q with a dot. So, just a quick recap of this brief introduction when we're talking about heat and heat transfer. Heat exists as an energy transfer due to a temperature gradient. This gradient always exists from a high temperature to a low temperature. And as we consider heat transfer, we're typically concerned about two things: the rate that heat transfer occurs, Q dot, or in some cases, as we're interested in developing design expressions or trying to figure out how to design heat transfer equipment, what's the necessary heat transfer flux for a given process, which we can then use to solve for area and design our heat transfer equipment. And so we designate that flux as the heat transfer rate, Q dot, over area, which in this class I designated as a lowercase cursive q with a dot. So we have three forms of heat transfer. What are those forms of heat transfer?
Conduction, convection, and radiation.
All right. There you go. 10 points to Gryffindor. We have conduction, convection, and radiation. Conduction deals with heat transfer that occurs via direct contact. Convection exists as heat transfer that occurs due to fluid flow, fluid motion. And radiation is heat transfer that occurs due to the emission of electromagnetic waves. In this class, we typically focus on conduction and spend a whole lot of time on convection. If we have time, we can discuss radiation. Radiation is pretty cool. It's really complicated and it delves into a lot of, gets heavy into physics, but it's also extremely important and valuable. And so we can visualize each of these three forms of heat transfer due to this image. We see essentially if we have a pot boiling water, we have essentially three forms of heat transfer demonstrated. Where if we boil a pot of water, what we can typically happen is the temperature gradients within the water cause currents to form, where the warmed water as it sits at the bottom warms up, it tends to rise. And then as it rises, it will cool, and then it will fall down. And so it creates essentially what's known as natural convection, which is convection that occurs due to the natural development of temperature gradients within a system. That differs to forced convection, where the fluid is essentially forced via like a pump or compressor, where you're inputting energy into the system to cause the fluid flow to occur, which is differing from natural, where the fluid flow occurs due to the presence and emergence of the temperature gradients that it can exist. We have conduction, where if you have the handle hot and you forget to grab the pot holder, and so you grab the handle, it burns you. That energy transfer happens from the handle to your hand by direct contact, which we state as conduction. And then you can have radiation, where you have a fire, that a fire emanates radiation, which can warm you primarily in the infrared range. And so you can have essentially all three forms of heat transfer. So any questions, things that I can clarify, go back, re-explain with what I've discussed thus far? All right. So let's talk a little bit about conduction. So as I stated earlier, conduction is heat transfer that occurs via direct contact. And so we have energy transfer by direct contact from high energy molecules to low energy molecules. Conduction is governed by what is known as Fourier's law of conduction, which states that the heat flux that exists via conductive heat transfer is a function of the temperature gradient that exists between the objects that are in direct contact and a corrective contact constant that identifies the anticipated heat transfer due to the temperature gradient that exists.
Is that dt, d lowercase t?
Now it's dt dx. And so if, let's say, we have 100 degree, let's say I have two slabs in direct contact. This one's at 100 degrees C, this one's at 20 degrees C, right? We have a temperature gradient that exists. And so we consider dt dx being the gradient that emerges in that direction. And so we can designate the heat and heat transfer as a flux, and that flux is directly related to the gradient by a constant of proportionality. This constant, K, is known as the thermal conductivity. This thermal conductivity is a measure of a material's ability to conduct heat. It's also important to consider that this is an intrinsic property. That is unique to each material. So what type of materials can we expect to have high levels or high values in thermal conductivity?
Metals.
So metals exhibit high values of thermal conductivity. Do you know what metal has the highest?
Is it tungsten?
It is not tungsten.
It's not gold, is it?
It is not gold.
Is it copper?
It is not copper. Copper is a close second. It's the one I expect students to answer because its value is so high.
Would it be a
Silver?
Would it be what?
Silver.
It is, in fact, silver. Which is why, if you study anything associated with electronics and hardware manufacturing, silver is used to assist in areas where thermal conduct is important. For those that may, be into PC building, that's why when you do CPU installation, you need what's known as silver paste to connect it to your heatsink. And so, just for added context, you can have a list of, some of the comparisons between metals. Tungsten's relatively reasonably high, gold's pretty high, and copper and silver are close. However, silver does have a higher thermal conductivity in pure performance. Comparing this to non-metals, you can see several orders of magnitude can exist. And in general, what we find is that liquids have a higher thermal conductivity than gases, and solids will typically have a higher thermal conductivity than liquids, just because the energy that can travel via conduction is much better when the molecules are close together. And so, as we compare here, we have, 100 to 16 watts per meter Kelvin. As compared to these materials, we're below essentially 1 watt per meter Kelvin as it relates to thermal conductivity. So let's look at an example. So let's say we have a 0.4 square foot single pane window that is a 1/2 inch thick, which separates a home at 75 degrees from a cold December day at 38 degrees. What is the heat transfer rate through the window if the thermal conductivity through the window is 0.6 BTUs per hour per foot per degree Fahrenheit? And we're just going to focus on that, ignore everything that says if the home is heated. We'll get there here in a second. So we're just going to look at an example of heat loss through a window. And so in this example, the window is, 1/2 inch thick. The temperature on the outside is 38 degrees. The temperature on the inside, somebody's cranked up their heater, 75 degrees. And so, based on the existence of the gradient, we know heat will go from the high temperature to the low temperature. So heat will be lost through the window from the inside to the outside. And we stated that heat flux is related to thermal gradient that exists by our thermal conductivity. I could rearrange this and say my heat transfer rate is equal to K times my area of heat transfer times my gradient. And if I was, instead of going to consider it in terms of the differential gradient, I can approximate it as a comparison between 2 points of interest, or I can say Ka delta T over delta X. And if I were you, I would probably keep this somewhere that you kind of can easily refer to it, because when we're looking at conduction, aside from the differential form, this is the form that we're going to be using most often. So, based off the equation that I have, where Q is equal to K times A times delta T over delta X, where K was given in the problem statement as 0.6 BTUs per hour per foot per degree F. The area of the window was 0.4 square feet. The temperature inside is 75 degrees Fahrenheit. The temperature outside is 38 degrees Fahrenheit. And the thickness, or delta X, of the window is 1/2 inch, which if I convert that to feet, should be very small, 0.04167 feet. So if I were to solve for my heat transfer rate through this window, I would just simply have to plug in these values, where I have 0.6 BTUs per hour foot degree Fahrenheit times the area of 0.4 square feet times the temperature gradient, or 75 degrees Fahrenheit minus 38 degrees Fahrenheit, divided by the thickness, or 0.04167 feet. This would give me a heat transfer rate of approximately, let me do this math, I'm getting approximately 213 we can check our units. And so we have 2 feet here. Cancels out this foot. The degree Fahrenheit gets canceled out here. So what we're left with is BTUs per hour. Is everyone able to follow along with that example okay?
Yes.
Yes.
Perfect. Yeah. So definitely keep this form of the equation in mind. That's what we use more often than not when we apply Fourier's law of conduction. There may be a couple times where we'll have to look at it in a differential form, but for most of these types of problems, you're going to see this delta form. So let's look at the next step of the problem. Okay, it asks now, if the home is heated by natural gas, which costs $1.50 per CCF, which stands for 100 cubic feet, and 1 CCF of natural gas outputs 1 therm, which is approximately 100,000 BTUs. I really didn't make up these units, they're real. What is the cost of energy lost through the window in a month? So this is one of those, stop, heating the neighborhood, cooling the neighborhood, kind of grumpy old dad type of things. You're wanting to know how much money you're losing. And so let's see if we can do this calculation. So we're going to consider the energy loss in a month. And so I know if this was a realistic situation, I would have to consider the average inlet temperature, inside temperature, the average outside temperature. But for the sake of the problem, we'll just assume on average the inside is kept at 75, the outside is 38 degrees Fahrenheit because it's Denver and it's December. And so we have to consider, yes. And so we need to know how many hours are in a month. So we're going to assume a 30-day month. So 24 times 30 is 720 hours in a month. Oh, thanks. Sorry. I thought I switched it over. So we're going to assume a 30-day month, which is 720 hours in a month, which means the total heat lost there
Why
is
wouldn't we do 31? It said December.
You know what? You're right. When you call me out, I gotta accept that. So 744 hours in December. So we have our 230 BTUs per hour times 744 hours in the month. And so we have 153,360 BTUs lost. So if I want to solve for the cost, I know I've lost 153,360 BTUs. I know I have 100,000 BTUs in 1 therm. And I know 1 therm is outputted by 1 CCF of natural gas. And I know 1 CCF of gas costs $1.50. So my cost is therefore this value divided by 100,000 times $1.50, or approximately $2.30 of energy lost in the window. And that's just assuming you have the 1 window. So not too terrible of a follow-up, but we'll keep this in mind. We'll actually do a follow-up looking at a comparison between a single pane window and a double pane window, so you can kind of see the difference in terms of heat transfer through both window types. But that's for another day. So any questions on conduction and how to apply Fourier's law in a system? Like I said, we'll look at probably more complex versions of Fourier's law on Wednesday and Friday. But just as kind of a quick overview, I want to provide you just a cursory glance at the application. All right, we can talk about the next section of interest, which is going to be in convection. So convection can be denoted as heat transfer that occurs by fluid motion. Another way to look at it and consider it is it exists as the enhancement of heat transfer over conduction due to fluid motion. And we look at this quite a bit when we do a deep dive in convection, where if I had to compare, let's say, a metal rod that's hot and I put it in a water bath, a couple things would happen. Initially, you would have conduction, right? Because it would just be a hot metal rod sitting in water. But over time, a couple things can happen. As that cools, you can have natural currents that exists as fluid rises and falls around that rod. We call this natural convection, or it's essentially the emergence of fluid flow due to temperature gradients. Another thing that we can consider is if we have a metal rod and we forcibly flow water around that object. And this, what we would consider, is forced convection, because we're essentially inputting energy to cause flow to occur. And we find that forced convection will definitely have the highest rates of heat transfer as compared to natural convection and typical traditional conduction. And even natural convection will have better heat transfer than simply conduction. And so when we consider convection, as we describe it as heat transfer due to fluid motion, a lot of ways to consider it is it also exists as an enhancement over conduction due to the existence of fluid motion and fluid flow. And so, cursory glance at convection. Convection is governed in part by what is known as Newton's law of cooling. And Newton's law of cooling states that the flux in convection is simply a function of the temperature gradient that exists times another heat transfer proportionality value. And we also consider this delta T, which we designate as T sub S minus T infinity, where Ts is our object's surface temperature, T infinity is also designated as the surrounding temperature, or the fluid temperature around the object. And H is known as our heat transfer coefficient. Now, the important thing to consider with heat transfer coefficients is it's an extrinsic property. Meaning it's dependent on both the material properties which means the objects which heat transfer is being transferred from, as well as the flow conditions. And when we really get into convection, heat exchanger and heat exchanger design, 80% of the effort typically comes in identifying the heat transfer coefficient, because it is a quest, to say the least, in some problems. One thing I also like to keep in mind is when we consider forced convection, we can also break this down into what's known as external forced convection and internal forced convection, where when we talk about, what we consider internal forced convection comes up more so, and that's what we focus on. External forced convection can occur in systems where you have flow through ditches, streams, things like that. A lot of civil engineering applications can exist as external forced convection. When it comes to process operations and chemical systems, internal forced convection is by far the standard. And so this is, essentially flow through pipes and heat exchangers. So do I need to zoom out, repeat anything? Are you guys following along okay?
Doing okay.
Great.
Doing okay.
So I think we have just enough time for one more example. So let's look at this system where if I have a 2-meter wire with a 10 centimeter diameter extending across a room that is at 20 degrees C, and we'll say that heat is generated in the wire due to an electrical current. So, it exists as a resistance heater. And the wire gets pretty hot, gets to 150 C. And so if we assume that the voltage and current generated is all going and being emitted as heat, what is the convective heat transfer coefficient between the wire and the air in the room? So actually, you know what? I'm going to give you guys some times and breakouts. This is a good problem to work together and talk with. So I'll give you guys 3-4 minutes to see if you can come up with the heat transfer coefficient.
Current is 0.5 amps.
Perfect. Thank you.
You guys add?
Hello.
Oh,
We were just going to ask for the problem because we didn't get all the numbers and the slides aren't posted on Blackboard yet.
oh, I'm sorry. Yeah, my bad. That is on me. Here's the problem. I'm sharing my screen with you now.
Okay.
Thank you.
Of course. Happy to help.
I can like screenshot it so you don't have to stay in here if anyone else asks for help too.
No problem. Yeah, I'm just going to start bouncing around, make sure people are on task. No worries.
Yes, sir.
All right.
But that's what I don't get. I don't know what units amps times volts gives you.
So,
Gives you watts.
Watts.
oh, okay.
Yep.
So that's how you
Oh.
get your Q, and then you just divide by surface area.
And by the gradient.
And by the gradient.
Yeah, the delta T. Then you'll get H. Your final answer should be in watts per meter squared per Kelvin or per degree C.
Is the flux pretty high?
The flux, well, it should be. It's a small wire, right? Well,
Yeah.
yeah, the flux will be pretty high.
Yeah, because I got 4,400 watts degree C.
For the
Well, shouldn't the flux be watts per meter squared?
Yeah, it's watts per meter squared.
Wait, how do you get the watts per meter squared?
Double check that. I'm going to bounce out. How'd it go?
We didn't get an answer in time.
No.
We ran out of time.
We did too.
I'm sorry. Well, I will work with it with you here in a second, and hopefully you will be happy with this problem and the solution. So this one is looking at a resistance wire. So I know Newton's law of cooling states Q is equal to H times A sub S times Ts minus T infinity. Now I said that the voltage is 110 volts. The current through it was 0.5 amps, which if I assume all that power is going into heat, then the heat, Q, is 110 volts times 0.5 amps, which is 55 watts. Now, it's a metal rod. It's 2 meters long, 10 centimeters in diameter. So if I assume this wire is only going to be emitting heat from the outer surface, and I'm ignoring the ends for this, I can say my surface area is pi times d times L, or pi times the diameter, which is 10 centimeters or 0.1 meters, times the length, which is 2 meters. I get an area, or approximately 0.628 square meters. So all I left with, I know the surface temperature is 150 degrees C. The room temperature is, what did I say, 20 degrees C. So with that in mind, I can rearrange Newton's law of cooling and write it in this form, Q over A sub S times divided by Ts minus T infinity. Or I have 55 watts divided by 0.628 square meters divided by 150 minus 20 degrees C. This leaves me with watts per meter squared degrees C. And if I do that math, I get approximately 0.67 for my heat transfer coefficient. So, any questions on that example? I'll try to keep in. Go ahead.
What's the formula for heat from like voltage and the amps? What is that relationship?
Voltage in amps gives you watts.
P equals IV from
Yeah,
physics.
P equals IV, yeah. P equals IV or V squared over R. There's one other I can't remember off the top of my head. So yeah, it's what you're probably missing is just the power is equal to volts times current for an electricity. Where if we're converting all that power to heat, I just assume that's what my Q is coming, where my Q is coming from. All right, any other questions?
What chapter are we in?
That's a fair question. This is, I believe, part of chapter 10. Oh, yeah, we're mainly focusing on chapter 10. But if I'm honest, the section of heat transfer for this class, we start bouncing quite a bit from in the book. And so most of this is going to be in 10. There's going to be maybe a couple pages in 11. But in terms of reading for this week, it will be from chapter 10.
Thanks.
You're welcome. Anything else?
Dr. Lopez, do you think you're going to be in office hours at like 11:15?
Yeah.
Awesome. Thanks.
No problem. All right. If not, then I think that's all I have time for today. Thank you all guys for attending. I appreciate it. And I also appreciate your
Thank you.
participation. I'm going to start, jumping in and out of breakouts to make sure we're all staying on task. But so far, you guys are doing awesome. I really appreciate it.
Thank you. Later.
All right.
Thank you,
Take
Dr.
care, guys.
Lopez.
Have a great day.